So, hello to everybody. Welcome to this talk. Thanks again, Francisco, and thanks, Eric, for the invitation. I'm very glad to be here to present today this talk that's going to be on surprises in the search for topological states in systems with gains and losses, also called non-hermitian systems. And so I'm very happy to be talking on this today. So to start this talk, I would like to use this quote from a famous movie that probably many of you have seen, especially the one that have a bit more that are older. So my mom always said that life was like a box of chocolates. You never know what you are going to get. And so I decided to start with this quote because it's a bit, it feels very much like what happened to us a couple of years ago. We started the project with a couple of young colleagues, and we were very excited about this project. We really had no idea of what we were going to find, and the feeling was very strange. We started with this guy, Victor Manuel, who was at that time, he was a PhD student in Brazil, in the northeast of Brazil. I met him in a conference. We were talking for a while, and he was a very curious guy. We started to do some calculations, and I said to him, "Why don't you try this problem? Let's check what's going on." And so we did a couple of works that had quite some impact. And suddenly, like in this movie, you start running in some direction, and suddenly you are among a bunch of other people that are running in the same direction, but really you don't know where you are going. And so it feels very much like in this movie, and so that's why I like to use this quote for introducing this work. And as well, you can see that in this picture, at least, it looks very much similar. So it's even better. This feeling. So before starting, I would like also to acknowledge collaborators, many people that I found along the way. For this work in particular, I would like to thank Victor Manuel and Esteban, and well, we are working also with these two guys, and Jose Eduardo, who is in Mexico now, got a permanent position. He was a postdoc with us. And these two guys that are working in these topics, but I'm not going to talk about their work, not in this talk. So thanks to all of them. Thanks also for all the institutions that are helping us and sponsoring us, University of Chile, Fondesit, and many others. I'm sitting, well, usually I'm sitting at the University of Chile, the campus of the Faculty of Mathematical and Physical Sciences. There are some pictures there, but well, by now I have been at home for a couple of months, so I really miss the workplace. So the outline of this talk is as follows. I will start with the motivation and a few reasons why to go to non-hermitian systems. Then I will talk a bit about the search for topological states in these non-hermitian systems with gains and losses. So I'll try to motivate why to go there, and what are the main challenges. And then I will talk about something that we found a couple of years ago, that is this anomalous localization effect produced by higher order exceptional points. I will explain what are these exceptional points that probably many of you don't know. I didn't know myself a couple of years ago about this, so I will introduce them very briefly. And then if I have time, I will connect with Floquet systems, and then the final remarks. So let's go with the motivation for this work. So as many of you probably have seen over the last couple of years, there has been a surge of interest in the physics of these non-hermitian systems. Here there are some papers you probably saw, many of them appearing, for example, in PRL, PRX, and they all have this non-hermitian in the title, and lot of stuff having to do with topological states. So for those of you who are acquainted with this area, you probably have seen already a lot of them. So these are here just a few examples that I took. Many of them are quite, have been really highlighted in their journals, except for our papers, all the others were quite highlighted in their journals. And here are some examples, a very personal selection of the very first. Now there are many more. Some are experimental. This was one of the first experimental papers in this area that appeared a couple of years ago. But I will show you during the talk many more that appear more recently, and probably you have already noticed. So these are some more papers dealing with this. Non-hermitian and topological appears everywhere. And so to give a flavor of where we are located, I like to use for this sort of things that are more experimental, kind of, let's say, newer. I like to use old maps because they reflect more the picture that we really have. It's not like using Google Maps where you have very, very precise idea of what's going on and where things are. Here it's more like an old map where the only thing you know is that you are getting a bit farther from the coast and that there are a lot of demons and strange creatures that may bring problems. And so if we think in this general area of topological states of matter, where we have things like the integer quantum Hall effect, and so this search for non-hermitian topological states is farther away from the coast and is one of the latest fronts that is developing. So that's why I use this picture. So very first thing would be to try to understand why to go to non-hermitian systems, why this fancy name, why to study these systems. Well, this in general, this has a very long history. I will just present a few main points, but there are really many studies. For many people, all this story started with these two guys, Bender and Botcher, who in 1998 essentially said, well, when we teach quantum mechanics, one of the first things we tell to the students is, the observable, the values that you can measure from an observable must be real numbers, so they must be real. And so to assure this, you ask for the operator associated to the observable to be an Hermitian operator. But these two guys said, well, we can probably relax this condition and still have real eigenvalues. And a way to relax this condition is to request for the Hamiltonian to have PT symmetry. And if the eigenstates happen to also have PT symmetry, then the eigenvalues are real. And well, all this story started there. It's a very fundamental point of view, trying to relax the conditions that we impose on our theories for developing quantum mechanics, essentially. So this is one of the possible motivations. It's not my motivation. This is a very fundamental viewpoint. We decided to get into this because of a different reason, and I think it's the reason that drives most of the people now. And the point is that non-Hermitian Hamiltonians appear everywhere if you think of them as an effective theory. So, for example, this is a natural thing in the description of systems where you have gains and losses, like, for example, photonic systems, microwaves, mechanical systems. So there, it's not that systems are necessarily quantum, but you have a Schrödinger-like equation description for them, and from there you get an effective Hamiltonian. And so this is what happens mainly in photonics, for example, many times, also in mechanical systems. And there, very pragmatically, you get an effective Hamiltonian that is non-Hermitian, and this is why many people are interested in this. But there are also many other sources of motivation for dealing with these systems. For example, for people like me that come from quantum transport, and then we have been dealing all the time during the last decades with systems that are open to quantum systems that are open to reservoirs where you inject charge, you take out charge, and so there it's very natural to have a Hamiltonian that is non-Hermitian, although with a lot of peculiarities associated to where you put the self-energies associated to your leads or contacts, and so that's one way. But there's also another source of motivation, that is that one might get an effective Hamiltonian that is non-Hermitian if you want to introduce in the very first approximation the effect of electron-electron and electron-phonon. If you do it in the simplest possible approximation and you introduce electron-electron and electron-phonon in a kind of poor man's way, using self-energies to take into account of the finite lifetime due to those interactions, then this is something that happens very naturally. So in this sense, it's also natural to think of non-Hermitian description. So as to summarize, there are a couple of reasons. In photonics, in mechanical systems, it's very natural to have this sort of effective Hamiltonians. In open systems, like systems that we deal with in quantum transport, it's very natural, or to describe the finite lifetime due to interactions. So all these reasons bring me to consider this sort of non-Hermitian Hamiltonians. But every time you get into something that looks new, a very first question is, what's truly unique of these non-Hermitian systems that I don't get in typical Hermitian descriptions? So what's really unique? Here, I would like to mention one point that for me is crucial, and this point is what people call defectiveness. So to introduce this, let's take this example of a very simple 2 times 2 matrix, like this one is 1, 1, 0, 1, and this matrix has a single eigenvalue, that is lambda equal to 1, that is an eigenvalue that has an algebraic multiplicity of 2, so it means that this is a second order root of the characteristic polynomial. But when you are going to look for the associated eigenvectors, normally for an Hermitian Hamiltonian you have as many eigenvectors as the degree of your eigenvalue. Here you get a single linearly independent eigenvector that is 1, 0. So this means that this matrix cannot be reduced anymore, and so you cannot take it to a full diagonal form. This is already in a canonical form, it's a Jordan form, and in this situation you say that this matrix is defective. Why? Because it doesn't have a full basis of linearly independent eigenvectors. So if you take all the linearly independent eigenvectors, you don't manage to span the full Hilbert space. So this property, it's a property that appears in this matrix because the matrix is non-Hermitian. For Hermitian operators, you are assured that you have a full basis set of linearly independent eigenvectors. Since this matrix is non-Hermitian, then these things may happen, and as in this case. Now, if there's something very interesting that appears that was put forward by Kato in this book that is called Perturbation Theory for Linear Operators. It's a book that appeared in the 60s, and that is called exceptional points. Essentially the same example I showed you before, you can carry it forward to a more complex system where you have H0 and V are matrices. H0 is Hermitian, and now what I do is I put this lambda here factor in front of the perturbation, and I let this lambda vary in the complex plane. If this lambda can change now in the complex plane for some specific values of lambda, that are those shown here, lambda 1 and lambda 2, what I see is that exactly at those points, 2 linearly independent eigenvectors suddenly coalesce. So not only the eigenenergies coincide, but also you get this loss of one linearly independent eigenvector. You had 2 eigenvalues that were different and had each one a linearly independent eigenvector, and suddenly when they coalesce, you lose one of these eigenvectors, and then the matrix becomes defective. At these points, you have what's called an exceptional point. This has been known for many years, and these points are what people also call non-Hermitian degeneracies. So it's a kind of degeneracy, but it's one of these truly unique things of non-Hermitian systems, where it's not only that the eigenvalues become degenerate, but you also lose linearly independent eigenvectors. So this is a very interesting thing, and so this is something that I would say should have very important consequences when you are considering, for example, topological states of matter, and so of any system described by a non-Hermitian Hamiltonian. And so, in contrast to what the people did a long time ago, in these last years, this surge of interest is associated to the search of topological states in non-Hermitian lattices. And here I emphasize this word lattices, because now what we think is something in the spirit of a crystal, that where you have a basis that repeats itself regularly in space. And in these systems that will now be described by a non-Hermitian Hamiltonian, what people try to do is search for topological states. So what does it mean to have a topological state in general? Well, when we talk about topological states, what typically a physicist, a condensed matter physicist, will be thinking is that there is an underlying boundary correspondence. So this essentially means that in this system, the bulk of the system, so what happens very deep inside the system, far from all the frontiers, will rule what happens at the boundary. So how many boundary states you will have, and this will render all the atomistic details of the boundary irrelevant. Essentially what happens is that you have the bulk that will be characterized by an integral property that is called the topological invariant, that typically has this shape. It's an integral over the labels of the eigenstates that is essentially the Brillouin zone, so it's wave vector space of some kernel. This kernel that you have inside will be something that is computed only from the eigenstates of the system, not the eigenvalues. So at the end of the day, what you will have is that this integral that you compute will give you a different flavor of information that is complementary to what you have in the band structure. In the band structure, you only plot eigenvalues. The information of the eigenvectors, eigenstates is never there. But with this so-called topological invariant, you will be able to give the flavor of what's going on with the eigenvectors. That's information that typically you don't put in the spectral properties. To say it with the fingers, what happens is that this object, the topological invariant, will somehow count the number of knots that you get in your bulk wave functions, and will be able to tell you if two different materials that look the same from the spectral viewpoint are really different or not when you cut edges into the system. So what tells you is that not all insulators are equal. Essentially, some have a topological invariant that is trivial, others have topological invariants that are different. And so when you, for example, the vacuum can be thought as a system with a topological invariant that is trivial. And so if I have a sample of some system and then I end it, I can think that I have a boundary with a vacuum. And so now I get a problem when I end my sample, because here very deep in the sample I have a well-defined topological invariant. Whereas on the other side, after I finish it, I have the vacuum, and the vacuum has also a well-defined topological invariant. If this topological invariant here is non-trivial, then I have to transition from this non-trivial value to 0 somehow. And how to do it? Well, what happens is that in between, you have to cut this figure, you have to cut this knot, and to cut this knot is to pass through a region where the topological invariant is not well defined, that is a metallic region. And so you need to have edge states that will bridge the gap of your system in between. And so this is why these states appear there, and they are robust. They have to be because you had, they have to be there because you had well-defined topological invariants very far away. So somehow as well you can think of this as a way to see some sort of non-local property embedded in these systems. And so this invariant is very important because can help you to predict the number of edge modes that you will have, chirality, etc. So what are the main challenges for finding these topological states, in this sense that there will be a boundary correspondence, as I just said, in these non-Hermitian systems? There are many challenges. I will mention here a few of them. You can look at the references where you will find more thorough account, but here I'll just mention them. The very first thing is that if you want to define a gap in a system, when you have a complex spectrum, so complex eigenvalues, you face the very first problem is that there's no order relation for complex numbers. So for real, while you are along the real axis, you can always order your numbers and say this number is before the other one. But if you are in the plane, you cannot do it. And so you have to somehow use some criteria. There are several proposals in the literature. This that I'm quoting here, it's one of them. There's another one that is more used today, that is this one, that it's bandgap can be seen as a prohibition of touching a generally complex base energy in the complex plane. So I have real imaginary part of these energies. I have a point here that I set it arbitrarily, and then I say that I have a gap if the eigenvalues of my system that are here in blue do not touch this point. And so if I'm avoiding this point, then I can say that with respect to this point I have a gap. And this is what people call a point gap in this literature. In the Hermitian case, it's easier because I'm along a single axis, and then I can always order my numbers, and then I have clearly a region where I don't have eigenstates, eigenvalues, and that's it. But here in the plane, I have to do something else. And so the first thing is this definition of point gap. It's one possibility of how to generalize this. I can also do a similar trick, thinking of, for example, a line. And so I can, for example, define a line gap as the prohibition of touching a line, arbitrary line that I can imagine. And so, for example, I can have these two sets of eigenvalues in blue that are separated by this line, and then I say, well, this is a line gap. And these are two different definitions, and so you see that immediately you have more things that could happen as compared to a normal system, an Hermitian system. And so this is one thing. A very first thing that you can see here is that weird things happen. For example, here I could have a gap defined in the sense of a point gap, even for a system that has a single band, because all these states might live. These states in blue might live in a single band, and I still can define a point gap. So this is very weird. This has no counterpart in Hermitian systems, in the band theory for Hermitian systems. So there are more strange things going on. One of them, and it's very scary for solid-state physicists like me, it's that there's an extreme sensitivity of the spectrum of the eigenvalues to the boundary conditions. So this means that essentially the spectrum that you get from a finite system may not match at all with that of the corresponding infinite system. What I mean is I take a piece of a sample that is described by some Hamiltonian that is non-Hermitian. I calculate the spectrum, all the eigenvalues, I plot it, and usually in solid-state physics you say, well, if I start making the system larger and larger and larger, at some point these two things will go to the same the same thing. The spectrum will coincide, and if you compute density of states or whatever, they will match. But in these systems, what happens is that you might have an extreme sensitivity to the boundary conditions. So what happens at the end is that, for example, you may have a system that every time it's finite, it's gapped, and when it's infinite, it's ungapped, or the opposite. And so this can seem, one might think this is nonsense. Well, in non-Hermitian systems, it's possible, and this defies everything we know for Hermitian Hamiltonians. And something related to this fact that we found a while ago is that a system, a lattice that is non-hermitian and ordered, pristine, no defects, nothing, may have all eigenstates anomalously localized at the boundary. So even those states that you may think, well, if the system, I make it large enough, at some point I will get states that are extended, and so I should have states in the bands that are extended. Well, in these non-Hermitian systems, one may have that all the states are localized at the boundary. And so this sort of strange localization, we called it anomalous localization in a paper a couple of years ago, and now, as I will show you, it has been rebranded. It's called non-Hermitian skin effect, in analogy with the skin effect for electromagnetic waves, and it's very weird effect, and I will show you what does it means to you right now. And so in particular what we have shown is that you may have this very strange sort of localization that will appear as a result of what's called exceptional points, as I defined before, but exceptional points of a very weird type, that is, they are higher order. They have an order that scales with the size of your matrix. So things that you have an n times n matrix with a single linearly independent eigenvalue. So this is a higher, this matrix has a higher order exceptional point. So a while ago what we did was to consider a simple model that appeared in a paper by Tony Lee in 2016. Was a simple ladder, as I show here. The details here are not very relevant because by now these sort of effects appear in many systems. So, but it was our starting point. This system is special because we have gains and losses. So this is marked with red and blue here in this plot. So the different sides, this is a system that is repeated. So it's a crystal of this, and you have gains on one leg of the ladder and losses on the other leg, and then you have some couplings in between. And this gentleman, Tony Lee, had the idea of this system can be described by a 2 times 2 Hamiltonian, then you can expand it in Pauli matrices, as I show here. And he had the brilliant idea of saying, well, I will choose the coefficients of these Pauli matrices in such a way that when I change k, I will encircle an exceptional point. And let's see what happens. And he was looking for topological edge states, as you find in many other areas. And this system is special because it has PT symmetry. It's a non-Hermitian system, but it has PT symmetry. So PT is a combination of parity and time reversal. So the Hamiltonian is invariant to this product of symmetries. And so we decided to re-examine this, and we decided to take a look. The very first thing that we did was to take a look to the localization properties of the eigenstates. This system has a spectrum that has a real part, as shown here, an imaginary part, as shown here, and I'm plotting here the spectrum as a function of B. B is this coupling here in green. It's the coupling between the legs of the ladder. And so you take the spectrum for each set of parameters, you plot it, and you have this. And here in color, what I'm showing, it's a measure of localization of the eigenstates. I'm showing this thing that is called inverse participation ratio, and that is essentially computed this way. So you take every point in the lattice, you compute the modulus of the wave function at that specific point at the 4th power, and you divide over the normalization for the eigenstates. So if you have a given eigenstate that is fully localized at a single site, then this gives you 1. But if this state is spread all over your sample, then you will have values that are very small. And why they are very small? Well, because since it is at the 4th power, this will decay very fast, and so you will have very small values. So large values of the inverse participation ratio will mean localized states, and small values will mean delocalized states. And what you see here when you plot the spectrum as the function of this parameter on this Hamiltonian, on this ladder, what you get is that all the states are in very deep blue. except in this region very close to v equal to 0, the rest of the spectrum is in very deep blue. This means that all the states are very highly localized. And if you look a bit more, and something else is that if you compute, this is for a finite sample, if I compute it for an infinite system, the spectra, they don't match at all. So it's an extreme sensitivity to boundary conditions I mentioned before. And for us this was a surprise, because in this paper by Tony Lee I mentioned before, he was interested in the states at zero energy, that typically is where you look for topological states. And he said, well, the edge state of the system is located at zero energy and is there. But when we looked more carefully, what we realized here, these are the different eigenvectors of the system as a function of position. This is just 30 sites. And what you see is that all you see that essentially all the weight is on a single side of the sample. So you get all the weight on a single side of the sample for all the eigenstates of the system. So this means that all the states became anomalously localized at the boundary. Even the states here that you say these are the bands, this was supposed to be the edge state, well, not all of them are edge states here. So this is at the beginning I thought this was completely crazy. Indeed, I told Victor Manuel, compute this again and try this, try that. Then I did it myself, and effectively this was true. I mean, all the states were anomalously localized there. If you look at this in a different way, what happens if this is imaginary part of the eigenenergies, real part, and this is exactly at this line here, where you see that at this line for v equal 0.5, all the eigenstates coalesce into 3 points. 1, 2, 3 points. And so here at the center you have an exceptional point of order 2, but these exceptional points that appear here are exceptional points of order n-1. N is the number of unit cells of the system. So you have exceptional points of an order which scales with the size of the system. This is something very massive. And essentially what happens is that all the information you had in your Hamiltonian gets condensed into this very small set of points. It's kind of aleph of the exceptional points, so everything got condensed into these very few points of that I showed you before. Why aleph? Aleph because of this quote from Borges. He has a very nice story that is called the Aleph, and this story is about a guy that lives in San Telmo in Buenos Aires, and he's a bit crazy. He says that in his cellar he's got an Aleph, and the Aleph turned out to be a very small object that condenses everything that ever existed on Earth. Everything, it's there, undiminished in this small object. And so somehow this is a sort of Aleph, but it's a strange Aleph. It's a sort of Aleph that really simplifies information, that loses a lot of information. Here essentially what happened is that a lot of information got lost, and you got some very handful of things that are condensed at these points. And here, to show the strange properties of higher order exceptional points, what you can do is use a measure of the departure from hermiticity. It's a bit mathematical, but it's simple. It's something that you may have seen in linear algebra. If you think of a normal, let's say, Hamiltonian H, you have eigenvectors, that these eigenstates that are here denoted by C alpha. But in the case of a non-Hermitian Hamiltonian, the right eigenvectors that are this mark here are in general different from the left eigenvectors that are these phi alpha. In general, these things are different, and so for Hermitian system they are the same thing, and so you can make up a measure of this departure from hermiticity that is called the phase rigidity. That is, you make the internal product between the left and right eigenstates and divide over the norm. And so what you get is that very close to hermiticity, you have this R alpha, this phase rigidity is 1, and in contrast, when you go close to an exceptional point, it goes to 0. because they are orthogonal. And for example, in typical studies in this field before with non-Hermitian Hamiltonians, like this paper by Aleph and Rother that is referenced there, I hope that you can see it. It's there. Well, you see the chair is 022117 2017, the page number. And you have, for example, here, this is the phase rigidity as a function of a parameter in the system. And typically, what you have is that close to an exceptional point, this departure from hermiticity happens very, very deep. It's a point where this shuts down like crazy and then recovers. And so even if the Hamiltonian is non-Hermitian, if you are a little bit away from an exceptional point, the system doesn't have this very unique property that are exceptional. This phase rigidity, it recovers immediately. So the effects seem to recover very fast. But in contrast, what we see in our system, because of these higher order exceptional points, is that I do the very worst thing I can do. I sum up all the phase rigidities over all eigenstates, this sum here, and I plot it as a function of a parameter of the system that is V, and I plot it in log scale. So what I showed you before was in normal scale. This is in log scale, and what I show is that this phase rigidity decays exponentially close to these higher order exceptional points. And even if I do a zoom and then increase the size of the system, this becomes even worse. So the larger I make the system, the more I get farther away from hermiticity from the viewpoint of the phase rigidity. So this means that there is a very pervasive consequence of the departure from hermiticity that appears in this non-Hermitian lattice. And it's an effect that is exponential in the system size. This was like really special when we saw it. We really wanted to have better grasp of this. And we look at many things. For example, we look at the rank of the matrix. When you have a matrix, the rank is the number of linearly independent eigenvectors. So exactly at v equal to 0.5, this goes to 3, because you only have 3 linearly independent eigenvectors. The matrix is very defective. But then typically what happens is that mathematically you have this effectiveness only over a set of points that has 0 measure. So it's very abrupt. But what happens? Because I have only 3 eigenstates, and suddenly as I move the parameters, I start to develop more linearly independent eigenstates. But if these eigenstates are very close to each other, I cannot distinguish between 2 linearly independent eigenvectors anymore. So what we did here is to compute the rank of the matrix with a tolerance to somehow simulate this thing that physically, even if 2 states are mathematically linearly independent, you cannot distinguish it if they are too close to each other. And what you see is that the recovery of this rank is very, very slow. Until you get to the maximum that here is 400, it's very, very slow. So this is quite anomalous, and what's happening there. Then we also checked what happens against disorder. Now you can put a lot of disorder in the system, and what you see is that the states keep being localized. So they are all in blue, and nothing changes very much. And so this is what we published in this paper. It's a paper that appeared in 2019. We submitted it in August 2017. It was a very long fight. They refused in PRL, then appeared in PRB as rapid communications. It was a very long fight to publish it because the results were quite strange. It's not the things that we do usually. We were getting into a different field, and so it was really, really long fight. Then what happened is that this effect was found again by other people, and for example in this paper, it's one of the papers that are most cited in this area. These 2 authors published this paper in August 2019. They submitted it well after our paper. It was like more than 6 months afterwards, they somehow found again the same effect that we pointed out earlier, so it was not previously overlooked, and they also found some very interesting analytics that are very nice, and they called it non-Hermitian skin effect. This name, non-Hermitian skin effect, is the name that is used pervasively in the literature to reference this. And another of the early references, it's this paper by Xiong, that it's almost contemporary with ours. This was sent on September 2017. Ours was sent in August of the same year. So these two are really very close to each other. And this is a very nice read. And by now, this effect, this sort of non-Hermitian skin effect, is recognized in the literature as one of the biggest issues in the area, this emergent area of the topological state of non-Hermitian systems, as you can see, for example, in this paper. And but one may think, well, this looks very mathematical. I'm a condensed matter physicist. I'm not a mathematical physicist, and so you could say, well, is any of this real at all? So this is a very valid question, and to our surprise, it is real. It appears in many systems. This is one of the very early manifestations of this that was reported experimentally. This appeared last year. It's Corentin Coulet paper, where they made a robotic version of a 1D system. So these are robots that are made with Arduinos and things, and they made a model for mechanical systems where they emulate a system with a non-Hermitian Hamiltonian, and they see this sort of analog of the non-Hermitian skin effect for this system. So this it starts to get more real. Then this is closer to my heart. This is an experiments that appeared this year. I think it was March or April. It's a discrete quantum walk of single photons, so it's photonic systems, and they see this anomalous localization known as non-Hermitian skin effects. This appeared this year in Nature Physics. Very interesting paper. So I recommend this very highly. It's a very nice paper. There's also a realization that appeared 2 weeks ago in Physical Review Research. Very nice paper by a group in Germany, where they realized an analog of this sort of Hamiltonians in a topoelectrical circuit, and they see this non-Hermitian skin effect. There's also a very recent paper that appeared in Science, where they call it topological funneling of light. But if you see here, it's essentially a manifestation of the non-Hermitian skin effect, but that they use here to funnel light. And so it's really a very hot area with lot of things going on. There is also this paper that appear also in Circuits. This appeared in Nature Physics in June. Also, they see this effect in topoelectrical circuits. And so it's really a plethora of experiments. So it's getting real. Now the question is, what are the consequences for the search of topological states of non-Hermitian systems of this sort of effect? That I hope that I have convinced you that it's real, in spite of being very unintuitive. And yes, there are many consequences. One of them is that the moment when you break this connection between a finite system and the infinite system, then you may expect some problems to build a bulk boundary correspondence, as I mentioned at the beginning. And this is something that has been worked out by many people with different strategies that I will not mention here, because there are really different strategies for doing this. And I'll just put the references. And I will go, because I don't have a lot of time, I will go just to a slide to try to interpret this weird idea of having defective Hamiltonian. So what does it mean to have a defective Hamiltonian? So this is something that was an obsession for me for some time. And so the best way to understand it that I have is this one. I think that you have an Hermitian lattice, as I show here. It's a very simple lattice, and I think that this lattice, for example, this could be a Chern insulator, so a system that only has states at the edges. Top edge moves from left to right, bottom edge moves from right to left. And suppose that to the Hamiltonian I add a condition, a boundary condition, and I say the particles that are getting in come from the left. So I put a boundary condition that the particles come from the left. If I do this, then I may be interested for some reason in considering not the full Hamiltonian, but just a slice of it, so a slice of this size, and describe it effectively. If I do an effective description for this, then I would be left with a system that is smaller, that is something like this, shown in B. And in this system, what I will try to condense is both the information of the initial Hermitian lattice plus the boundary condition, that I say the particles come, for example, from the left. And when I do this, what happens is that I do something that is really very unorthodox. That is, I'm putting in the same object the information of what is the usual Hamiltonian and the boundary condition. It's different from Lippmann-Schwinger, where I put the boundary condition somewhere else. What I do here is I put the information in this single object that is the effective Hamiltonian. Now, what I can think, if this object here was a Chern insulator system with a state on one side and another state that is chiral on the other side, now what I have is that instead of having the two of these states as possible eigenstates of this effective Hamiltonian, what I have is that I only have one of them. Why? Because there's only one of these two states that is compatible with the boundary conditions that the particles come from the left. So will be only the state on the top edge, the one that will be compatible here. The other one will be lost because it's not compatible with the boundary condition. So in this sense, the effectiveness can be interpreted as the lack of compatibility with the boundary condition. And essentially, this is what happens in these non-Hermitian Hamiltonians that could be seen as descriptions of systems that are now out of equilibrium, and these out of equilibrium conditions will enter as a boundary condition in a weird way in the effective Hamiltonian. So with this, I'm getting to the end. I hope that I have convinced you why non-Hermitian systems and lattices in particular can be of interest. I've signaled a few of the challenges in the path for getting topological states in this type of systems, and especially I showed this effect of anomalous localization in non-Hermitian lattices, and highlighted the role of these higher order exceptional points that can be, this effect at the end can be interpreted as well as an environment mediated interaction effect, as we put forward in these papers. And so this is essentially what I wanted to show you, but the story goes on. There's more and more. For example, very recently we have also seen that this non-Hermitian skin effect, this anomalous localization effect, can also be traced to a topological origin. This was put forward in these two papers. One is still unpublished, the other appeared in PRL this year in February, where essentially they find that the topological invariant, that is the vorticity, that is now the winding number in the energy space in real imaginary space of the eigenenergies, gives probably some topological origin to some of these systems. And so with this, I would like to finish, and thank you once again for your attention. Questions? Yes.